In this video, we're picking up where we left off with our Calculus 1 final exam review. And we've got just a couple other examples of limits that need to be evaluated without a calculator. Now, prior to this, we were evaluating limits at specific values, and this time we're evaluating limits at infinity. And this technique could also be used to describe infinite limits as well, or limits that equal infinity. Now, the instructions are written in such a way that it reminds you that you can use pre-calculus techniques to answer a few of these questions because we're talking about asymptotic behavior. And especially with rational functions, we discussed asymptotes quite extensively in college algebra for this reason. If you recall your rules for establishing asymptotes, then recognizing horizontal asymptotes is going to be particularly helpful in this case. If I've got a rational function that's written as a fraction as such, and we recognize that the numerator and the denominator have the same degree, then we might recognize that the graph itself has a horizontal asymptote at y equals the fraction created by these two coefficients. So that's 4/12 or 1/3. And so if we're thinking about what we did in pre-calculus, we would go through a bunch of analyses and find the vertical asymptotes and the holes, but eventually we would identify a horizontal asymptote, in this case 1/3, and we would recognize that the graph itself, I don't exactly know where the vertical asymptote is, so I'll guess that it's here, but the graph itself will flatten off or tend towards this particular value. Now, if we're trying to answer the question, what's the limit as x approaches infinity? Well, that's exactly what's being shown here by this graph. As x gets larger and larger and larger, we would like to know what the y value is as it gets, as the x value gets larger and larger. And in this case, we see that the y values are flattening off or leveling towards 1/3, and we've identified that by using our understanding of asymptotes and rational functions. So, the instructions do say to show appropriate work to justify your answers. You could go through the entire process of sketching this graph, or you can do what I've done here and identify the degrees of the numerator and the denominator. Now, in a related method, not quite exactly the same, but it's related, and we can be a bit ruthless here. For part B, we recognize that we have the limit as x approaches infinity of x cubed over an expression, and we're being asked to find the square root, or to consider the square root of 16x to the fourth power plus 9x. Now remember, it would be entirely inappropriate to say that the square root of 16x to the fourth plus 9x is equal to 4x squared. That would be wholly wrong and incorrect. However, as far as function behavior goes, the values, square root of 16x to the fourth power plus 9x, tends towards 4x squared. The behavior of this function is very similar to the behavior of this function. And as we're talking about limits, we can essentially get away with that notion. And the square root of this 9x business, well, that's inconsequential because it's so much smaller. The square root of 9x is so much smaller than 4x squared. This 4x squared is what's describing the behavior of the function at large. Much like when we encounter a polynomial, we only concern ourselves with the leading coefficient and the degree of the polynomial. We don't really care what's happening after that to determine the polynomial's end behavior, or how the polynomial behaves towards infinity. So if this is the general behavior of the function, then it's clear to see that the numerator, x to the third power, is going to grow at a faster rate than the denominator, 4x squared. And again, knowledge of our rational functions indicates that the numerator degree being larger than the denominator's degree implies that there is no horizontal asymptote, and therefore this function is either approaching infinity or negative infinity. And so, in a sense, we have a positive result in the numerator as x approaches infinity, and we have another positive result as x approaches infinity in the denominator. And so I think it would be fair to say that this function approaches infinity. The numerator grows at a faster rate than the denominator, and both approach positive numbers themselves. And so the result of an extremely large value divided by a large value is still infinity. In part C, we again can apply sort of this ruthless approach to evaluating limits. As a transcendental function, e to the x power, as x approaches infinity, we recognize that this component itself will approach infinity. And same down here, this number approaches infinity as well. And so if you're thinking about this from just a general perspective, the numerator is growing towards 2 times infinity, whereas the denominator is just approaching infinity plus 1. And while this plus 1 or plus any constant has virtually no effect on the value of infinity, it's relatively nothing compared to infinity, we might recognize that the limit result here in a direct substitution of sorts is going to be 2 times infinity divided by infinity, which would then be 2. And in our last example of this group, now a couple of these techniques are formalized in our textbook, and we didn't spend much time talking about them, but if you would like to find the formal descriptions as to why some of these techniques work, take a look at Chapter 6. That's where L'Hopital's rule was introduced, as well as this notion of growth rates. That's essentially what we use to answer B and C. And then also what we're going to use for part D, this notion of a bounded limit. For part D, cosine of x, it's going to oscillate between between negative 1 and 1. And so what I'm going to point out here is that we've got a limit of cosine of x multiplied by the limit as x approaches infinity of 1 over square root of x. Now this limit in itself is indeterminable. We don't know what the result of the function will be as x approaches infinity because it oscillates between positive and negative 1. There's no one single answer for that. This guy, on the other hand, will equal 0 because as 1 remains constant and the denominator increases towards infinity, the square root of infinitely large numbers becomes an infinitely large number in and of itself. So 1 divided by that is going to be 0. And as it turns out, the product of a function whose limit is known times a indetermined, or I should say a bounded limit will also equal the result of the product of those limits. Although I can't quite say that in general. I mean that a limit that approaches 0 times a bounded limit will equal 0. So because this limit is equal to 0, and even though that this limit is undefined, the product of 0 and undefined will end up being 0. And so computing limits in general can be quite difficult if we consider them their own series of math problems. Fortunately for us, our focus on limits has been interpreting them in the sense that we can use them to answer some questions about calculus, about rates of change and accumulated change by way of derivatives and anti-derivatives. So while some of the limit questions may be a bit challenging on this exam, rest assured that the primary focus of this exam is to determine your understanding of derivatives and anti-derivatives. So let's get into some of those for the next portion of this review. In question number 4, we're given some function. We don't know what the function is, but here's the shape of it. And we would like to know some information about the function itself. At which of these points is the derivative positive? Where is the derivative negative? Where is it equal to 0? And then on the next page, I guess that's it. I thought there would be more because the instructions said A through E. But 3 questions, that's all that there are. Well, you should recall that a derivative is positive when the graph itself is sloping upward. The derivative is negative when the graph of the original function is sloping downward, and the derivative is 0 when the graph itself appears to level off. So during your test, if there's any question on what the point is implying, or what the position of the graph is implying, please let me know. Like I know some of you might look at point B and might ask, well, is that at a flat spot in the graph, or is it at a point where it starts to slope upward? And if that's your question on the test, I'll be happy to clarify. For me, I would argue that A and B are both locations where the graph is sloping up. C is a location where the graph is leveling off, and D and E are points where the graph is sloping down. So to say that the derivative is positive at A and B, I think is a good answer. To say that the derivative is negative at D and E is a good answer. And to say that the point or points where the derivative is equal to 0, C would be a good answer. Now, if you were thinking that B is at a spot where it levels off, then you could move this answer B from the first group to the last group, and I would still give you credit. Of course, I can't give you credit if you label it twice, but if you didn't have the answer B here, but you did include it down at C, I think that would be perfectly fine and acceptable as well. So for this next question, labeled number 8, we're given graphs in the right column that are derivatives of graphs from the left column, and we need to match each function in the left column with its derivative in the right. So if I were approaching this, I would look at the graphs on the left and start considering what the derivatives ought to be, and I just pick some arbitrary points to do that. So in this particular case, A, if I look at all of these different x values and then consider the slopes of the function at each of the y values associated with them, I notice that all of these derivatives are negative, and they're becoming less and less negative as the graph moves to the right. So this position here on the far left, we had a really negative derivative, and this position was still negative but less negative, and so on. So if I had to take a guess here, I would think that the derivative should look something like this, and I would look for that on the options on the right-hand side. And as it appears, this particular function does have the derivative indicated there. In this second example, I would do the same thing. Here's an interesting point because this is where the graph levels off, here and here as well. So in each of those cases, I would say that the derivative is equal to 0, and I would mark that derivative right here at 0 on the y-axis. Then I notice something that's kind of interesting, that to the right of this point and to the left of this point, the slopes are all positive. And while it's slightly positive here at the beginning and slightly positive here at the end, it's rather steep here in the middle, so it's going to be significantly more positive. And this looks like an inflection point to me where concavity changes. So that tells me that the derivative has to reach a 0 at that point as well. So I think the graph of the derivative should look something like this. Now as far as the next region goes, in between these 2 points, it's very similar, if not identical, to the sketch of the derivative on the left. But they're all negative, right? All of these slopes are negative. And then if we consider the behavior of the tails, well, or the far ends of these tails, here again we're back to a positive derivative, just slightly positive, still positive, but it changes inflection. So I think we're going to reach a high point right about here and then down below. The steepness of this graph along this region is nowhere near the steepness of the graph here. So therefore the height of the derivative should not be as tall as the height of the derivative over here. And if I were to finish sketching that derivative, I think it would look something like this. And now I'd be on the lookout for that elsewhere, and it looks like we found that match up here. So go ahead and try these last 2 on your own. Which functions seem to be the graph of these functions' derivatives? You can resume playback in a moment to check your work. So in these examples, if you chose not to use the technique that I did a minute ago, you could also just consider in general what's the behavior of the derivative going to be. And in this first region, the derivative is clearly negative. It looks like it reaches 0. The steepness here might be 0. And then it turns to a negative derivative again. And then in this region, we've got ourselves a positive derivative. And so if we're looking for a graph that represents that, negative values, 0, negative values, and then positive values, well, that matches this graph down here. We've got negative values. We've got a value that reaches 0, negative again, and then transitions to a positive value. So it looks like we're increasing. In this particular example, all derivatives are positive. Throughout the entire graph, the slope is positive, either slightly or more positive along the way. And sometimes we see this graph and it looks like it gets infinitely steep right here in the middle. And that's not the case here, but the behavior of the derivative is quite similar. If that graph had gotten infinitely steep, we probably would have seen a derivative that does this, where there's an asymptote on the derivative in the center, if it's impossible to calculate the slope of an infinitely steep line. Now for the last example of this video, we're going to use the limit definition to help us find the derivative of this particular function. Certainly we could use derivative rules, but we can't forget the process that was used to get us here. So we're going to do at least one or maybe two problems in finding the limits using the limit definition. Slopes. We'll find slopes using limit definition just to illustrate the concept and your understanding for that. Of course, this is one limit definition. The other one, perhaps more common that we've used in this class, the limit as h approaches 0 instead of x approaching a of f of x plus h minus f of x divided by h. That definition would be fine for you to use as well. Now clearly there's not enough room to show that work here, so I am going to jump off to the side and complete this example on lined paper. And I'll do this using the traditional notation that we use mostly in this class. And so I'm going to try to calculate or at least show what f of x plus h is first. We'll complete this and simplify it first and then write it in its limit definition. So here's f of x plus h, and we should simplify this. And after we distribute, we get 2x plus 2h plus 1. Now this will need to be squared, which can be a bit challenging. I'm going to do this one off to the side. I'm going to use the grid method to make this happen. I don't know if you've seen this before or if you've used this in the past, but I like this rather than distributing several times to make the product happen. So I'm just going to make a quick grid here. I know that 2x, 2h, and 1 have to multiply by 2x, 2h, and 1. So I'll just find all of their products here. And the nice thing about this grid method is that typically if there are like terms, they present themselves across the diagonal. So here I've got two like terms. Here as well I've got two like terms. And then this 2x and this 2x are like terms that can be combined. And so after I collect all like terms and combine them, it looks like this is the expression for f of x plus h. Now all of that was needed, of course, because our limit definition of the derivative requires the limit as h approaches 0 of f of x plus h, so this first group, and try to give myself plenty of room to work here. And I just recognize that it would have been nice to have this one foiled together as well. So in doing so, we get 4x squared plus 4x plus 1. I've indicated that here. So we've got ourselves f of x plus h in this group, and we're subtracting from that f of x per our definition, and all of that's to be divided by h, which of course we can't directly substitute at this point because the 0 in the denominator. But if we combine some like terms and look for items that will factor themselves out or cancel, we might be in a pretty good position. So I see 4x squared and 4x squared here. 4x, 4x, 1, and 1. Those all will factor out or cancel to 0 while adding. Additionally, I notice that the remaining terms, 1, 2, 3 of these terms, contain an h with them, so those can disappear. And we can now say that the limit as h approaches 0 of 8x plus 4h plus 4 is going to be the derivative function, and as h approaches 0, we end up with 8x plus 4. And we may have lost sight of this, but the whole reason why we were using this technique is because the derivative of the function x is equal to the result, and we're now claiming that the derivative of f of x is equal to 8x plus 4. And now that we have the derivative, we could use that to find the derivative at this particular point on the graph. To finish out this video, let's just consider what the derivative would look like using derivative rules. And in this case, we need the chain rule. So the derivative of f of x would be equal to 2 times 2x plus 1 times the derivative of the interior, which is 2. And after we distribute and combine like terms, we end up with 4 times 2x plus 1, which is indeed 8x plus 4. So before we knew all of our derivative rules, we would have had to go through the derivative definition using limits, and as it turns out, both are indeed the same. And in both cases, we can evaluate the steepness of the graph at an x value of 1, and once we know the steepness there, we could find the equation of the tangent line using the point-slope formula. So if you have questions on the remaining components, finding the slope of the graph and then utilizing the point-slope formula, please let me know. And any other questions along the way in this video, feel free to reach out to me as well. Thanks for watching.